It's my distinct pleasure to introduce Peter Bartlett. Peter, you can get ready to share your screen in a second. Peter's coming to us from UC Berkeley, where he's the Associate Director of the Simons Institute for the Theory of Computing. And he's the principal investigator on two large NSF-funded centers that are very resonant with our theme today, namely the Foundations on Data Science Institute and the Collaboration on the Theoretical Foundations of Deep Learning. So he's going to speak to us today about benign overfitting. So take it away, Peter.
Rich, this is several pieces of joint work among this set of authors with Phil Long at Google, Gabor Legoshi at Pompeu Fabra, and Alex Ziegler, who's a PhD student at Berkeley. You know, we've heard the story about overfitting, you know, being observed by practitioners in deep learning, and this surprising phenomenon that deep networks can be trained to zero training error, even for a regression loss. So you're really interpolating the training data and still give good predictive accuracy. One point that I'd really like to emphasize, you know, I think having the number of parameters large compared to the sample size is common in non-parametric statistics. Having a perfect fit to training data is not contradictory with classical statistical learning theory, unless you're in a noisy setting. And you know, that's the thing that's really striking here. I mean, you know, perhaps this was always taken for granted, but you know, there's noise in every problem. But without noise, you know, those things are certainly consistent with the statistical theory. Surprising thing is, you know, these experimental observations, and you know, this is an example from where I first learned about this phenomenon, an example from a paper that a bunch of people then at Google worked on, where noise is explicitly added to a training sample. In this case, one of the CIFAR vision classification problems. Noise is explicitly added, and yet this interpolating solution that's fitting the noise perfectly is still giving good predictive accuracy. On the x-axis is the level of noise in these two plots, and in the bottom plot on the y-axis is the prediction error, which degrades only slightly as noise is added. That I think is the really striking thing. You know, and of course this phenomenon's been widely studied and observed in a lot of other settings. Okay, so you know, that there's this surprising lack of a need to have a trade-off between the fit to the training data and the complexity of the prediction rule, even though this prediction rule is fitting perfectly to noisy data. So that's certainly overfitting in the sense that you're predicting better than you would expect from the noise level that's in the data. If the noise level was 0, you would expect to have a perfect fit if your function class is rich enough to contain the truth. But with a non-zero noise level, getting a perfect fit means you're overfitting, and yet this overfitting is benign. Okay, and you know, I think we've seen that this sort of lack of a trade-off between the fit to the training data, perhaps measured by the sample average of the squared error and the complexity of the prediction rule, which you can measure in lots of different ways, you know, is something we classically expect, and we teach to our students. You know, it's important to have this trade-off, particularly when you're in a non-parametric setting. It's important. You know, this is something that we've classically tried to avoid. And again, you know, the pictures here are when there's noise in the data. So, you know, I think that's a very fascinating phenomenon, and there's been a lot of work in this direction. So, you know, a lot of folks here have contributed to that. You know, rather than pointing at specific contributions, I want to take a kind of high-level synthesis of the results that we have for this phenomenon of benign overfitting. And many of these, I think all of the results have the flavor of you know, a decomposition, right? So cases where we know that that overfitting is benign correspond to a decomposition of the prediction rule into two pieces. A simple component and a spiky component. A piece, the simple component is a piece that's useful for prediction, and the spiky component is the piece that's useful for fitting to the noise, but in a benign way. So it's the benign overfitting component. And our classical statistical learning theory applies to, you know, the simple piece, and it's this overfitting piece that's really fascinating. Not useful for prediction, but it equally doesn't harm prediction. So this perspective, you know, just to advertise, there's a review paper that Andrea Montanari, Sasha Ruckler, and I have written that's appearing in Acta Numerica soon that takes this perspective. Okay, so one example that I think is very nice as an illustration of this this sort of perspective, and one of the first examples where we could understand this this phenomenon is a classical non-parametric statistical estimator, the Nutaria-Watson estimator, but with a really unusual kind of a kernel. So in a kernel smoothing setting, we take our XY pairs, we make predictions according to a weighted sum of the Y's that we've seen, and they're weighted in a way that depends on how close the point X is to the training pattern XI. Where this closeness is measured by a kernel K, there's a bandwidth parameter H that affects the extent to which, you know, how locally or how distant the impact of an XI is going to be. So we have these weights, which are, you know, for our positive kernel, the ratio of KH at X minus XI divided by the sum over all of the, perhaps this should have been an index J, the sum over all of the training points of the KHs. And the striking thing is that you can come up with an interpolating prediction rule of this flavor, and this was work done by Belkin, Raklin, and Sibakov, and Belkin, Su, and Mitra. So you can come up with a kernel, a rather non-standard kernel that actually goes to infinity at 0 because of this norm to some suitable power alpha on the bottom here. It's a compact kernel, but it goes, you know, has this spiky point at 0, which means as you approach the training point XI, you know, this weight goes to infinity, and you have an interpolating solution, right? So F hat at XI is equal to YI, but nonetheless, you can get minimax optimal rates with a suitable choice of the bandwidth parameter. Okay, so that's a really striking example, maybe an unusual kind of a approach to take in this Nutaria-Watson estimator, but you know, very much fits into this perspective that you can view the prediction rule F hat as having two pieces: a simple component that's essentially due to the rather standard compact kernel, and a spiky component that's useful for overfitting. The spiky piece is something that has a small norm in L2P. The approach, you know, this is a linear estimator in the sense that the predictions are linear in the Y's that we see. The approach that the talk that I'm gonna give is really concentrating on the case where the F hat is actually a linear function. So we're looking at linear regression setting. So the outline for my talk today is looking at a characterization of when overfitting is benign in a linear regression setting under some assumptions on the problem, and you know, we'll be precise about those in a moment. I want to say a little bit about the implications for sensitivity to adversarial examples, and then talk about some recent extensions to ridge regression. Actually, Nicole mentioned some of these results in her talk a moment ago, and then look at some limitations on classical statistical learning theory sort of analysis in understanding benign overfitting. All right, so that's the agenda. Let's start with linear regression and a precise sort of formulation. We'll give some definitions that we'll use throughout most of the rest of the talk. Okay, so we're thinking of this case of predicting real valued responses y given a covariate vector. You can think of that covariate vector as lying in an infinite dimensional space, but I'll be using matrix vector notation, so you could also think of it as being a Euclidean vector. The conditions we require are these xy pairs are sub-Gaussian, they're mean 0, and we're in the well-specified setting where the conditional expectation of y given x is a linear function. And of course, there's noise. Oh, and one other thing we need is that the x satisfies a small ball condition, so that the distribution of the x's is in some sense spread out, suitably spread out. Okay, so some other notation we'll use, the covariance matrix for our mean 0 x's is capital sigma. And we're thinking of the spectral decomposition of that, and these eigenvalues of the covariance are crucial. These are the lambda i's in decreasing order. Lambda 1's bigger than lambda 2, and so on. And there's the best parameter vector, the one that minimizes the expected squared error of our linear predictions, and sigma squared is the prediction error, the expected squared difference between the actual outcomes and that best linear prediction rule. All right, so this is the noise level, this little lowercase sigma squared. All right, so this is the notation that we'll need. We're considering here a particular linear prediction rule. It's the minimum norm interpolating rule. So our data you can think of as a matrix with n rows. This is the covariate matrix of covariates x, a vector y of responses, and our estimator is the one that, subject to minimizing the squared error on the training data, minimizes the length of the vector theta. And you can write that, you know, in terms of instead of the classical ordinary least squares x transpose x inverse x transpose y, it's a pseudo inverse, right? There are we're in a high dimensional setting here, and you know, it may be that this is a low rank matrix. This empirical covariance, scaled empirical covariance matrix is low rank. In the directions where it's deficient, we just set everything to 0, and in the other directions we consider the inverse. Okay, so that's the estimator we're looking at, and the criterion of interest here is the excess risk, the excess squared error. So the amount by which the squared error of this minimum norm interpolating linear prediction rule exceeds the best possible, the optimal prediction error. That's the error of this theta star. And it's easy to write this difference, this excess risk, as a quadratic form. It's just a quadratic form in theta hat minus theta star. Theta star is the best linear prediction rule. Theta hat is our minimum norm interpolating rules parameter vector. And you can see, you know, the directions where we've got to get things right are the large eigenvalue directions. So, you know, these lambda i's, the big values of lambda I are the directions where we better get this theta hat correct. And in those other directions, the ones with small values of lambda I, we can be more relaxed about our estimates. Okay, so so we're interested in this minimum norm prediction rule. We're thinking of the case where you're in a high dimensional setting and able to interpolate the training data exactly. Classically, you know, this is a lot like a ridge regression setting where we have a term that involves the fit to the data and a term that involves the scale of the parameters. But we're thinking about really emphasizing this term and having paying infinitesimal attention to this term. So it's like having lambda go to 0, where we want to nail the fit to the data and subject to that constraint, minimize the norm of the parameter vector. So we can view this as the Lagrangian of a constrained minimization, where we optimize the data fit term subject to a constraint on the norm of the parameter vector. And of course, the solution to this problem with an appropriately chosen B is the same as the solution to this problem. Similarly, we can think of it as, and this is the setting we're thinking of, the minimum norm subject to a constraint on the performance on the data. But here we're thinking of, taking an extreme view of this constraint. We set C to 0, or more generally set C to be something much smaller than the best we could hope for here, right? What we should hope for here is a parameter vector that's something like the optimal. This is a sample average of the losses. There is a minimal value of that that we should expect there, and that's the noise level, the expected squared error of the optimal linear prediction rule. So we're thinking of the case where we're doing a much better fit than we should expect to exist. Okay, so that's the overfitting regime. We're looking at an extreme value of this constraint. And considering the situation where we're in a high enough dimension that actually we can get that constraint down to 0, that data fitting term down to 0. So having it down at 0, of course, with a squared loss means we're nailing it, right? Our prediction is exactly the value that we see on each of these n training points. So we're taking all of the noise that's embedded in each of these labels and that's in each of these labels and embedding it in the parameter estimate. And we'd like to know when that doesn't hurt prediction accuracy. So here's the theorem. Under the conditions on this linear regression problem with these parameters theta star, sigma squared, and our covariance matrix capital sigma with its eigenvalues lambda 1 to lambda p, I guess maybe p is infinite. The result depends on a couple of notions of effective rank. This little rk of the covariance matrix is the effective rank of the covariance after you've dropped off the first k heaviest eigenvalue directions. So the k directions that have the highest variance form a subspace. If we look at the orthogonal subspace and ask, what's the effective rank of the covariance in that orthogonal subspace, k star is the dimension that we have to, dimension of the subspace we have to skip before that effective rank gets as large as the sample size n, or a constant times the sample size n, a universal constant. And once we get up to that k star, so there's the upper bound is that the excess risk of this minimum norm interpolating prediction rule is bounded by two terms, a bias term and a variance term. The k star better be small compared to the sample size, and we have another notion of effective rank that should be large compared to the sample size. Effective rank of exactly the same, orthogonal subspace, and of course the noise level arises here. There's a converse result that says you shouldn't expect to do any better than this apart from perhaps a constant factor. Here we've got slightly stricter conditions on the problem. The X here has the same covariance matrix, but it's with independent, a lot of independence. You can express these covariate vectors as a linear transformation of a vector with independent components. For instance, if X was Gaussian with the given covariance. And the theta star that we're considering in order to get the matching bias term, we're considering a theta star that's a symmetrized version. So the theta star I, each component, has the same magnitude, but randomly flipped sign. And in this case, we get exactly the same quantity in here. So, we shouldn't be able to improve this upper bound without without further assumptions, by more than a constant factor, I should say, without further assumptions. The bias term, I'm kind of skating over it. We actually saw this in Nicole's slides in a slightly different setting. This involves the parameter vector, the magnitudes of the components of the parameter vector. And one thing that's interesting here is that the bias that we see involves a term that looks at the optimal parameter vector in that subspace orthogonal to the K star subspace. It's as if we're predicting 0 in that orthogonal subspace, right? So that's one crucial thing to notice about the bias term here. Okay, so what are these effective ranks? Little rk is a 1 norm divided by an infinity norm of the remaining eigenvalues, the ones that you see after you chop off the k heaviest directions. And capital RK is a 1 norm squared divided by a 2 norm squared. All right, so this is a particular notion of effective rank. This one is how many times can you fit the biggest eigenvalue into the sum of all of the others. These are closely related. They can't be too far from each other. Capital RK is the bigger one. And you can think of it as, so certainly if you have a complete symmetry, so an identity matrix or a scaled identity, these effective ranks are just the actual rank. If you have a finite rank matrix, then you can express these effective ranks as the rank times some notion of symmetry that varies between 0 and 1. And in the two cases, the little rk symmetry is defined in terms of this 1 norm versus infinity norm. In capital RK, it's a 1 norm versus a 2 norm. Okay, so that's to give a bit of intuition about these notions of effective rank. Excuse me. So if we go back and look at the theorem, it's saying that the remaining directions after you drop off these k highest variance directions, the remaining directions, there are many of these remaining directions, a large number compared to the sample size, and they should be symmetry, right? We should have them roughly equally balanced. Or the more symmetric things are, the weaker this condition is. Okay, that the K star better be small compared to the sample size, and this capital R K star notion of effective rank should be large compared to the sample size. So we need lots of these directions, a large number compared to the sample size, that have this roughly equal variance in order to get the excess risk small. Okay, so in terms of this intuition that I mentioned at the start, our linear prediction rule here neatly decomposes into these two parts. The prediction component corresponds to that K star dimensional subspace, the highest variance directions, right? The biggest values of these, the biggest of these eigenvalues of the covariance matrix. And the benign overfitting part, the spiky part, is this orthogonal subspace. And it's benign when this n over RK star is small, right? So the effective rank in that subspace should be large compared to the sample size. Okay, so the intuition here is, I guess the result arises from the mix of eigenvalues serving two roles here. We've already seen the second of them, how the errors in our estimate affect the prediction accuracy. So, the high variance directions need to have a very accurate estimate. The low variance directions, it really doesn't matter what we predict. But the other role that these eigenvalues play is how the noise in the Y's gets distributed in the parameter space, into our parameter estimates. We want that noise energy to be distributed across lots of unimportant directions. That's kind of the key message here. And when you're able to do that, then you can you can overfit in this way without hurting the prediction accuracy. So of course you need lots of unimportant directions in order to have benign overfitting. And I think I've said all of these things, lots of non-zero eigenvalues. They shouldn't be too weighty. You need lots of small eigenvalues, and if they're roughly equal, that's even better. The more asymmetric they are, then the more that we need. Okay, so let me give a quick overview of the main ideas in the proof. We split things into a bias term and a variance term. The bias term is the excess expected loss that arises from the component of the y's due to the truth. The variance term is the excess expected loss from the noise, the contribution to the excess expected loss from the noise, you know, these two terms cause kind of corresponding distortions in our estimate. The first term, the signal part, is because we don't get a perfect perspective of the covariance of the x's. The second term is because we've got noise that we're embedding in our parameter estimates. And that first term, you know, is really rather straightforward to deal with. This arises in classical analysis of high dimensional settings, you know, where the dimension is large compared to the sample size. You know, settings like that have been studied for decades. What's new here is that we're taking the noise in the y's and putting it into our parameter estimates, and you know, that's a really it's really striking that this is not having necessarily having a bad impact on prediction accuracy. So that's the big question. You know, how do we keep control of the impact of that noise? So, you know, when we split the y's into the signal part and the noise part, we're going to just focus on the noise part. So split those y's. This is the noise part, and it's the impact of that noise component that's going to matter. It doesn't matter equally in all directions. It depends on which directions have high variance. Okay, so there's a signal part I'm going to ignore, and there's a noise part that arises from this piece of the y. And when we look at that, you know, we write our covariance matrix in terms of these eigenvalues and split things into the heavy directions, the ones with large eigenvalues, and the light directions. This condition about the effective rank is all about the concentration of the smallest eigenvalues of our sample covariance matrix. So, you know, we're in a high dimensional setting here. Our sample covariance matrix is a much higher dimension than n, but we're only ever going to see n directions. Because we take a pseudo inverse, we're considering the minimum norm interpolating solution. We ignore all but those n directions that we see in the data, and you know, this condition is enough under the sub-Gaussian assumption to ensure that all of those small eigenvalues are concentrated around a single value, the sum of the eigenvalues below the kth largest. So, you know, when you so what that means is that, you know, this matrix is in some sense well conditioned, right? It's got lots of zero directions, but in the non-zero directions, we're always above this level. The eigenvalues of our sample covariance matrix are always above this level. Thinking about the Gram matrix, you know, it is positive definite and bounded away from zero. And that's a lot like a ridge regression setting, right? A ridge estimate would take our sample covariance and fatten it up to this level rho, so that in all directions, you know, we're nice and stable. Taking the pseudo inverse leaves some directions as zero, but in the other directions, we have something that's at least at this level rho. Okay, so, you know, you can think about where the energy from the noise in the y's goes. In one of these VI directions, these are the eigenvectors of the covariance matrix, you get a noise energy in that direction that's proportional to n times lambda I. when we look in this VI direction, it gets scaled by this X transpose X pseudo inverse thing by no more than rho to the -2, right? If it appears in the theta hat at all. And then its impact on the prediction error gets scaled by another factor of lambda I. And so, you know, this is the bound on the excess prediction error that's attributable to that noise component. It's the noise level times another factor of lambda I times rho to the -2. In the high variance directions, you know, we can do a little bit better. The heavy directions, we can actually get things down to a 1 over n level. Sum things up over all of those directions, and you get the k over n plus n over rk of sigma in this upper bound, precisely where that arises. Okay, and the lower bound, you know, you can use a similar argument to understand where things come from there. Okay, so that's the result. One thing we can ask here is what sort of situations, you know, allow these quantities to be small, suitably small, so k star over n plus n over rk star. When is that going to be small as the sample size grows, right? So, you know, it's a little intricate because the rk star depends on the sample size, right? Because the definition of k star depends on the sample size. In order to simplify things, so we're talking about, you know, the asymptotics of this sort of result. In order to simplify things, we're going to consider an upper bound on the bias that applies to any finite norm theta star. So when we impose that upper bound on this bias term, you know, we can ask this question, well, for what kinds of covariance matrices do we have nice behavior as the sample size grows? And we're putting an upper bound on the bias term here that's applicable to any finite norm theta star. And then we're just asking, you know, when does the limit of this quantity, when is the limit of this quantity 0 as n gets large? So we can actually ask things a little more generally and say, not just in an infinite dimensional setting, but in a setting where we consider perhaps increasing dimension, right? Perhaps a sequence of covariance matrices as the sample size grows. You know, when do we see this quantity, which within a constant factor is the excess risk? When do we see that going to 0? Okay, so, you know, it turns out if you think about a polynomial decay of eigenvalues, then it's really a very narrow range of covariance matrices for which you see nice asymptotics. The eigenvalues need to be summable because of this first term, but they're just at the edge of summability, right? We have the only polynomial rate, it's not even a polynomial rate, the only near polynomial rate of decrease of the eigenvalues is I to the -1 times 1 over some log factor. So, you know, it's rather striking that we need a very specific pattern of eigenvalues in order to have this nice asymptotics. But, you know, it turns out that there are, if you consider finite but increasing dimensions, then you have a much richer kind of set of conditions under which the overfitting can be benign. So one example is very quickly decreasing eigenvalues plus some sort of isotropic component in our covariance matrix. So there's an epsilon n here, noise in all directions, and you know, very quickly decaying, let's say exponentially decaying eigenvalues, and we're stopping at dimension p. So if p is large compared to n, and the total energy, isotropic energy, is small compared to n, so epsilon n times pn is small compared to n, but not too tiny, then you have benign overfitting. You can make that quite quantitative. So this is a much more generic phenomenon. Another setting, rather than having a constant level of variance in all directions, you can think about having a slowly decaying eigenvalues that you truncate. Excuse me, truncate at some point. And again, the dimension needs to be large compared to the sample size, but not too large. And for suitably slow decay of the eigenvalues, and you're in good shape. Okay, so if we consider finite but large dimension compared to the sample size, then this looks like a much more universal phenomenon. Okay, a couple more things I wanted to say, just very briefly. There's been this phenomenon of adversarial examples in deep learning, sensitivity to adversarially chosen perturbations in the inputs. You can find directions so that a very small change in that direction of an input image, say, will lead to a very different output in a very different prediction for that example. In the linear setting, it's totally obvious where this sensitivity comes from. We're taking this noise, which is energy proportional to the sample size, and we're embedding it in theta hat. So we should expect theta hat to have a component that's very large in some direction, a component attributable to the noise that's very large in some direction, because this is a growing magnitude with the sample size. It gets in that direction. We take that noise vector. It gets injected into the parameter estimates. That gives us a direction where a change of x in that direction is going to lead to a huge response, and you can show a lower bound on that sensitivity that gets large. Epsilon here is the upper bound on the excess risk. So if we're in a benign overfitting setting, then the sensitivity to small perturbations in the input is huge. It's 1 over this square root of epsilon. Benign overfitting is inevitably tied to huge sensitivity in a specific direction in this case. This is just another perspective on this view as a decomposition, right? The benign overfitting component necessarily has a large L infinity norm, because we're fitting to the data precisely, but its L2P norm is small because it's benign. Okay, let me say a little about extensions to ridge regression. So this is joint work with Alex Sigler. In the ridge setting, when lambda is 0, this is exactly the problem we were looking at before. This was our minimum norm estimate. We're writing it in a kind of redundant way when lambda is greater than 0, so that we can express both cases, the interpolating case and any level of regularization in the same way. So we'll write a subscript lambda for the ridge regression coefficient to represent the solution to the ridge regression problem with coefficient lambda. The point here is that we can deal with this whole spectrum from the interpolating case all the way up to levels of lambda that correspond to classical kinds of levels of regularization. It's a whole spectrum of overfitting, and you can it turns out understand how things go across that whole range of solutions. The bounds on bias and variance again are within upper and lower bounds are within a constant factor. You can get these bounds for any lambda, and what happens is that these effective ranks, so anywhere that the sum of the tail of the eigenvalues appears, it gets augmented by the regularization coefficient. One striking thing that comes out is that if you think about the solution to this problem as being x transpose x plus lambda I inverse x transpose y, then it turns out there are cases where the best value of lambda in terms of the excess risk is negative, right? You should be counteracting the bias in the covariance estimate that arises in some cases. So if you have a setting where your covariance estimate is very far from the truth, then you can correct that with a negative lambda, improve on that bias without significantly increasing the variance. So that's something that certainly doesn't arise in a classical setting. And this is the result. As I say, everything's just with lambda inserted everywhere. You have the sum of the tail of the eigenvalues. Okay, and one last thing, I guess I have plenty of time. So one last thing is about the some more recent work on limitations of classical statistical learning kind of analysis. So this is really a result that rules out a whole lot of model dependent bounds. So, just taking a step back and thinking about the sorts of analyses that we're used to in understanding the performance of a prediction rule, we have an algorithm. It produces a prediction rule F. Perhaps its performance on training data. So this is the sample average of losses for some notion of loss. Let's say squared error is small. And that prediction rule is simple in some sense. Maybe it's a deep network, and the parameter matrices in that network all have small spectral norms. So we can get a bound on covering numbers of functions in that class, for instance. Right. So it's simple in some sense. It's got good performance on training data, and we'd typically like to know, well, when does that mean we can get an upper bound on the risk of that function, the expected loss, in terms of these properties of the function. Maybe it's these small norms of the of this deep network representation of the function, and perhaps in terms of the sample size as well. Okay, so there are lots of approaches to doing this. A lot of them are based on uniform deviation bounds. So the simplest of those are just uniformly across the class. You'd like to say that the sample averages of these losses are close to expectations. And if we have an upper bound of this form, so the epsilon here depends on properties of the prediction rule F, and capital F is the class of functions that have those properties. If we can say, maximizing these deviations between sample averages and expectations across that class, we never get bigger than this function epsilon, presumably it depends on the sample size, then, having a small sample average implies we're going to have a nice small expectation. Our risk, the expected loss of our predictions, is going to be small. So this is a classical approach. There's been a very nice example that Vaishnav and Rico Colta came up with, Vaishnav Nagarajan, involving a classification problem, particular input distribution. It demonstrates that uniform convergence results, two-sided uniform convergence results of this form, can't help in some of these interpolating situations. So they looked at a particular classification problem, a single gradient step for this problem, effectively a naive Bayes algorithm, gave a function that has perfect performance on the training data, and actually, this is a situation where this prediction rule predicts accurately, the performance is good. But because of the symmetry of the data distribution that they chose, you can show that any uniform convergence result, any uniform deviation bound of this form, a two-sided bound, for a class of functions that contains the function that you see, or other functions that you'll necessarily see with the same probability because of symmetry. You necessarily have a large value of this supremum of deviations. So, naively applying this sort of approach to get a bound on this quantity for a class of functions that's big enough to contain the prediction rules that you actually use in this problem, is hopeless, right? They necessarily, it's far from the sort of gap that you should be seeing, because this method demonstrates benign overfitting. Okay, what I want to tell you about is a result, I guess a similar flavor. It's in a prediction setting, linear regression setting again. It's not relying just on two-sided deviation bound, uniform deviation bounds, but actually anything that looks only at properties of the prediction rule. So if we want to come up with any model-dependent bound, so anything that looks at the prediction rule that a method comes up with, let's say also is a function of the sample size and perhaps some confidence parameter, we'd like it to be a uniform bound in the sense that for a large family of prediction problems, the excess risk is below this bound. This is the quantity we defined earlier, the expected loss minus the optimal expected loss. We'd like it to be upper bounded by this quantity epsilon with high probability. And we'd like that to be true for all suitably nice distributions. So let's say sub-Gaussian. Okay, a couple of other technical definitions. We might expect this sort of a bound to have a nice dependence on the sample size. We might expect as the sample size grows, things get better. In fact, all we're insisting is that as the sample size grows, things don't get too much worse too quickly. So in doubling the sample size, in going from N1 to N2, which is no more than twice the sample size, we might want, we're going to insist that our bound doesn't get bigger by more than a constant factor. Okay, we might expect it to decrease. This is saying it doesn't increase by more than this sort of, at more than this sort of rate. And the other definition we need is a notion of kind of density of sample sizes. So if we have a set of sample sizes with some property, we say that that set is strongly beta dense when we get above a certain size. That means that, up above that size, if we look at a set of size square root n, so up above n, we look at a set of size square root n, the proportion of values of n that have that property is at least beta. All right, so there's sort of a notion of most elements of an infinite sequence having a certain property. So that's what strongly beta dense means. And the theorem, this is joint work with Phil Long at Google. Theorem is that there's a sequence of distributions on a sequence of growing dimensions that are nice. The covariate distribution is Gaussian. The response distribution is sub-Gaussian. And for that sequence, if you have any bounded anti-monotonic uniform model dependent bound epsilon, then the least norm interpolant has very nice performance. The excess risk of this quantity in this this sequence of regression problems goes down like 1 over square root of n. So we're certainly in a benign overfitting setting, but nonetheless, for almost all sample sizes beyond a certain point, the probability that our bound is anything like this 1 over square root of n is small, right? So with probability at least 1/2, our bound is bigger than some constant, when it should be like 1 over square root of n. Okay, so anything that depends only on the properties of the linear prediction rule and doesn't increase too rapidly as a function of sample size is necessarily a bad bound in some rather nice situations. So it rules out a sort of whole avenue of analysis of this benign overfitting phenomenon. As I say, natural joint distributions. Yeah. Okay, and very quickly, let me give just the idea of the proof. The point is that benign overfitting relies on a random design, and if you look at what happens on the training sample, those are actually bad estimates, right? They're bad estimates because we're fitting to the noise exactly. So the distance between our estimate at a training point and the truth is of order the noise level. All right, so you know, we expect a sort of standard deviation error at the points that we're interpolating. So you know, we use a Poissonization approach to show that there are two situations, both nicely sub-Gaussian, that are essentially indistinguishable. One where the training sample, one where we're in this setting of predicting badly because we're relying on our performance on the training points, and one where we're in a nice benign overfitting situation and the training sample has measure 0. And you know, you can't have a bound that's valid in both cases when they're essentially indistinguishable. It needs to be big to cope with this case, but then it's very loose in the second case. Okay, so just to summarize, you know, this is this interpolation setting is you know, really fascinating new direction, new phenomenon. In the case of linear regression, we've seen a characterization where the noise that we're taking from the labels and putting into our parameter estimates gets hidden in lots of unimportant directions, and that's an if and only if. You know, we need to have lots of unimportant parameter directions. We've seen when we look at the requirements on eigenvalue decay that actually we get a much more general situation where benign overfitting can arise if we look at finite but high dimensional data. There's this inevitable connection to sensitivity to perturbations, adversarially chosen perturbations of the inputs, in the sense that if you are in a benign overfitting situation, you have huge sensitivity in this linear regression setting. We can extend things across that spectrum from interpolation all the way, all through, you know, all levels of overfitting up to classical levels of regularization for the ridge regression setting. And we've seen that many avenues of kind of classical statistical learning analysis of these kinds of problems are ruled out in this benign overfitting setting. So, you know, I think the exciting open direction is understanding this sort of phenomenon in nonlinear cases. The cases that are understood really are essentially linear. I mean, I think there are the neural tangent kernel results, the random features results that we heard about this morning. But you know, going in the nonlinear direction, I think is really fascinating, and I guess one exciting question there is whether we can get us see a similar decomposition into a classically simple component and a benign overfitting component. All right, I'll stop there.
Wow, thanks a lot, Peter. This is Rich again. Yeah, just great, really insightful, really interesting. Thanks so much. We have at least 2 questions up in the Q&A. And I believe that Arna is enabled to speak. So how about you ask your question, Arna?
Yeah, hi, can you hear me?
Yeah.
Yep.
Yeah, hi, thank you for the interesting talk. I was actually kind of excited to see your results on the eigenslope decay, eigenspectrum decay, because it's something that has been recently observed in the field of neuroscience, specifically in the mice visual cortex, that the neural codes in the mice visual cortex follows this exact 1/n property. So, which pretty much is what you are claiming should happen, or we need to in neural networks. I was wondering if you actually explored this in a multi-layer neural network setting, trying to see if this 1/n decay kind of holds across layers when we train like a multi-layer neural network, because effectively that's what we believe happens in, let's say, the brain. It's a hierarchical system, so we would expect some sort of multi-layer training to be happening and this property to be holding empirical in multi-layers networks.
Yeah, no, that's a really interesting direction. I'm not sure I understand exactly. It's the covariance matrix of what that decays like 1/n?
So if you actually record from the neurons in let's say a particular layer of the visual cortex, you would actually find the covariance matrix of the neural code, so the neural activity to follow this 1/n spectrum.
I see. So in a multi-layer network, we'd be thinking of, you know, the representation up to that point as being fixed, and then you're doing a linear prediction
exactly.
and seeing a certain covariance matrix. Yeah, right. Okay, that's really interesting. Yeah, you know, this is in some sense the random features model for you know, understanding neural networks and what goes on there. So there has been work in that direction. There, and it was mentioned in the first talk this morning that this exact asymptotics has been computed for models of that sort in a paper of Song Mai and Andrea Montanari. So there, you know, actually the this f hat splitting into a simple piece and a benign overfitting piece, you know, the same thing arises in that setting as well. I mean, the decomposition there is into you know, the same subspaces, but now they're polynomials, right? So it's the simple subspace is the dimension, the, you know, polynomials of a degree that you can estimate with the sample size that you have, and then the orthogonal component is kind of everything else that's useful for overfitting, but not for prediction. So yeah, I mean, this is that sort of that sort of perspective on a two-layer network at least. But yeah, fascinating that the covariances are measured to have this sort of property.
Yeah, pretty interesting that there are some parallels that from the theoretical side to, let's say, the experimental side in like biological networks. But yeah, thank you.
Yeah, thanks.
Thanks so much, Arna. That's yeah, great question. Our next question's from Daniel. I think you've been able to speak.
Yes. So you extended the analysis to general ridge regression and pointed out that in some cases, actually a negative penalty is optimal. And I was wondering if this suggested whether there are regimes where the minimum norm solution is in fact the optimal solution.
Yeah, exactly. So you know, the optimal in the sense of, so when I say negative lambda, that doesn't make any sense, right? So when you look at the original optimization problem as, you know, the original ridge regression problem as minimize the average of the squared loss plus lambda times a norm squared. If you put a negative value of lambda in that, you want to take theta off to infinity, right? In some direction to get this negative quadratic term minimized. So it doesn't make sense to have negative lambdas. I guess all I'm saying is if you then express the solution to that problem as a with the convex case of that problem as a x transpose x plus lambda I inverse x transpose y, then for that formulation, a negative value of lambda might be optimal, which, you know, it's a monotonic relationship. It tells you that the right level of regularization is 0 in those cases. So when you're in one of these situations where you've got a very a big jump at the K star step, then which means, you know, effectively the eigenvalues that you're going to see in the remaining directions are nice and large, then you know, having a 0 value of regularization is exactly the optimal thing to do. And the reason it's optimal is that you're you know, any higher level of regularization is hurting the bias and not helping the variance in any significant way. You've already got the variance under control because of that big jump.
Right. So essentially, the answer to the question would be these regimes where the optimal value is negative, you impose a constraint on that it's not negative, and then the optimal value is 0.
That's right. Yeah.
Yeah. Okay. Cool. Thanks.
Okay, great. Thank you so much for the questions. There's one question from Umberto there at the bottom that you may choose to type something out quick, Peter, but unfortunately we're going to move on to our next speaker, but that looks really quite interesting. Can you see it, Peter?
I can, yeah.
Okay,
So
perfect.
I'll process that when you're introducing.
Okay, thanks so much. So let's give Peter a thanks by our virtual means, and we'll get moving on with our next speaker. But just before that, don't forget to head out to the TOPML swag store. Right, we have a flash sale on TOPML baseball caps, so you might want to pick up your TOPML baseball cap.